It's astrophysicist from CEA, and working, of course, in James Webb University now. His career is started with a very different subject. With a very you online. Yes, please. Pierre-Olivier's career started with a very different subject, with a very notable, important work on cosmic rays. He did his thesis with Catherine Cesarski, and they published a notable paper on cosmic rays, theoretical, calculating the limits, the energy limit of high energy cosmic rays from supernovae, where they showed that high energy above 8 or 10 TeV cannot come from these remnants. You correct me if I am wrong. This is one of the best cited papers on this subject in '83. And then he turned to infrared, developing cameras for ESO, and especially he was PI in Vizier camera for the VLT. Correct me anytime I'm wrong. They made very nice, in his career working on infrared cameras, made very nice discoveries, like the form of the Beta Pictoris disk, the dust in the supernova remnants, and even the comet that fell on Jupiter. He has been director in different periods of the astrophysics department in CEA. His work on infrared, on dust, on the dust around suns, led him to naturally to planetesimals and then to planets. So he's now very interested. His work is interested in exoplanets, as he will show us in the GWST work today. He's co-principal investigator of the MIRI instrument, and this is what he's going to tell us about.
Thank you very much for the introduction and for the invitation. I'm really pleased to have this seminar here. So I will tell all you want to know, I hope, about James Webb. So let's start first. Why James Webb? Oh, have you done anything? I can no longer. What? Which one? Yeah. Oh, okay. So one aim is to go further away, earlier in time, and Hubble did a very good job. And you can see as a function of years. Here is time going from the present to 200 million years after Big Bang. And you can see how far we have gone with Hubble. But Hubble has reached a limit, a physical limit, because it is working in the visible and very near infrared. And because of the expansion of the universe, the light emitted, the first light emitted by galaxies or stars are shifted towards the infrared. So to go beyond what has done Hubble, and especially one interesting region which has never been observed is what is called the end of dark age, when the first star and the first galaxy were formed. And to observe this region, we need a larger telescope and a telescope detecting the infrared light. And this is the James Webb Space Telescope. So the idea I just developed was as early as in the 90s, beginning of the 90s. So it was clear that a telescope of the size of a primary mirror of 6 meter size, what was needed. And in terms of infrared, it go from 0.6, which is still visible, to 28 microns. So more than the size of the mirror, what is more interesting is the coverage array, the array of this mirror, which is 25 square meters. So it's the size of a PhD studio apartment, so just to have this kind of. And it is always say that it is the successor of the Hubble telescope, but as it is in the infrared, it is also the successor of the Spitzer telescope. And Spitzer was really a small telescope with a mirror of 85 centimeters to be compared with 6.5 meters. So there is a really huge improvement in the sensitivity going from Spitzer to James Webb, almost 2 orders of magnitude. And having this infrared telescope, not only we can go and see the first light and ionization in the universe, but we can follow the assembly of galaxies, the birth of stars and the protoplanetary system, and study the exoplanets. This is a 4-teamed. So what can we learn when observing the infrared? So apart from going and see the first galaxy and stars, you can also go through the clouds. So this is an image of a visible image. You can see in the sky. If you are lucky enough to see the Milky Way, you can see zones which are very dark. And when you are looking in the infrared, you can go through this cloud and see what is behind, and you can see a lot of stars. And it is also important when you are studying the star formation, which the star formation is within clouds. So you need to go in the infrared to see really star forming. Of course, another advantage of the infrared is to look at the emission of objects at a relatively low temperature. You all know the Planck formula, and with James Webb going to 30 microns, you can see very cool objects. For example, exoplanets. This is and another, I think, very important topic, and people, and I will show you some nice images. But for me, it is also a very valuable spectrometer, and a lot will be learned through spectroscopy because molecules have a lot of features in the infrared and in various environments. I will concentrate on the exoplanet later on, but you can have really physical diagnostics thanks to spectroscopic observation, especially in the infrared. It is a list of molecules with a feature in the infrared. So that's another reason to go in the infrared. So James Webb is a flagship mission from NASA, but with the participation of Europe and Canada. Europe has provided the launcher and Ariane 5, and also in terms of instrumentation, there are 4 instruments, 3 NIRCam, FGS, NIRSPEC in the near infrared from 0.6 to 5 microns, and 1 instrument in the medium infrared, MIRI. So this spectrometer was provided by ESA and done by the industry, and the MIRI instrument was done by Europe and the US. It was a 50-50 share, and was done in space laboratories, and that's where we participate in this MIRI instrument. In addition, ESA has 15 staff which are at the center of operation, which is at Baltimore, at the STSCI, which was also the center of operation of HST. So that means that Europe has guaranteed time, at least 15% of the James Webb observing time is for European. So, because at the beginning I was hearing that all will go to US. No, it's not true. We can have time. And in fact, during cycle 1, we did even better than 15%. We were at the level of 30%. So the instruments are relatively complex. There are 17 observing modes possible. So this is the wavelength, from the visible to mid-infrared. And you can do some classical imaging. You can do some coronagraphy. That means canceling the star light to see what is around, for example, exoplanet. And you have a lot of spectroscopic mode, very interesting. Single slit classical, but you have an integral field unit, and you have also multi-object, which is very powerful. You can do a spectra of 100 of objects at the same time with near spectrum. And it's very important for looking at galaxies, for example. You can have an image and then open some slit where you want to have spectrum. Very powerful. So it has been a very, very challenging to have such a telescope deployed in space. First, we had the launch. I was lucky enough to be at Kourou, and we had to look at the launch by an Ariane 5. It was a Christmas day in 2021. And what is amazing is how well the launch was. Of course, you have a nominal trajectory, and of course, you have margin, possible margin. And what happened is that the parameter was extremely close to the nominal one. What are the consequences of that? Yes, the Hubble was not needed to correct trajectory. So there are propellant for 26.5 years instead of 10 years. That means the lifetime will not be limited by this and could be limited by other factors. But taking into account this possibility, now CEA is very careful in operating the telescope, for example, the wheels, or there have been some meteorites. So now we look in the region of the sky where the primary mirror cannot be hit directly by meteorite, for example, to have this huge telescope in operation as long as possible. And it could be as long as 26 years. So that was the launch. Another thing which has been perfect was the deployment. Here you have the telescope in the Ariane rocket. It was completely packed, and he has to deploy once in space. And it is the first time there is such a deployment. So you can see that the primary mirror is made of 16 hexagons. And was really challenged, and this is part of the delay, was the deployment of this huge thermal shield, which prevent the sun and even Earth light to hit the telescope, because this is an infrared telescope and he has to be cool at a very low temperature. The temperature is minus 233 Celsius, which is obtained passively. There is no need of machine to cool down the telescope to such a temperature. And everything was working very well, and it achieved the temperature which was predicted. The last thing, 1 month after the launch, was to be in orbit around the L2 point. The L2 point is a point where the gravity from Earth makes a complement to the gravity from the sun, and the angular velocity at this point is the same as the Earth. So there are Sun, Earth, this point are always aligned, which is very important to have a thermal shield the smallest possible. Otherwise, you should have a very, very large one. The next step was to align the various hexagons, because a huge difference, for example, to previous observatory, is that the final shape of each hexagon is given by adjustment after launch, which means that the telescope, the primary mirror, could be very not thick, very thin, and the weight of this primary mirror is lower than the weight of the Hubble mirror, because it is very young and it is very thin. But you have 7 actuators behind each hexagon, and you have to phase, because if you don't phase, you have 18 images. That's not what you want, of course. And everything went very well. So then you have the commissioning and of the 4 instruments, and especially Miri. I was at STCI for the commissioning of this instrument, which has been done by the various European countries, including France, of course. And here you can see the various images in the focal plane of the telescope. So each instrument can observe in parallel with the other, but not the same field. So you cannot look at the same field in parallel with several instruments, but you can use several instruments in parallel. And one thing is that the image quality is better than the requirement. So we have really an excellent telescope. The specification was to be diffraction limited at 2 microns, and it is diffraction limited at 1 micron, so much better. Another thing important for the sensitivity is that the transmission is better than the requirement. There were some provision for contamination, but care was really made not to contaminate the mirror. And there have been also possibility to clean the mirror just before launch, so that the transmission is excellent. And another very important thing, especially for observing exoplanets, is the stability of the telescope, no jitter. The jitter is less than 1 milli-arcsecond, and the specification were 4 milli-arcsecond. So again, everything is going in the right direction. And this is an image I like a lot. That's an image of the MIRI instrument. You can see what was observed previously, the same field. So that's, and this is what we are seeing now with MIRI on James Webb. So no need to speak much about the difference in terms of sensitivity and angular resolution. So all going in the right direction, the sensitivity is much better than expected, which is not often the case when you commission an instrument. So, for example, the requirement was around 11 nanojensky, and before launch we know that it would be better than that. So the estimator time calculation was given 10 nanojensky, and in fact that measure could be 7.3. Same thing for the other instruments. So a very good instrument on the university. And to give an idea of how complex it was, and usually you have 50 single point failure for a mission. Single point failure, that means that if it fails, the mission is and in fact you had more than 6 or 7, what is usually the case. So that's really a very good, it was a challenge, and everything went. And then the scientific exploitation was able to start. And this is the first deep field observed with James Webb. It's only 6 hours of observation. And already in this image, there are galaxies which are further away than what Hubble have found. So with a few hours, we can do better than HST. We took weeks to get the further object in the universe. So many scientists use this first image to calculate the number of objects of galaxy very far away. At the beginning, the calibration was not perfect, and a few wrong claims were done, but there have been more observation, and especially spectroscopic observation. So the first image I have just shown was for everybody. There are other programs, so there are various ways to get observing time. As we have developed an instrument, we have guaranteed time observation. It's not much. It's 450 hours for a MIRI European consortium. There is the director at STCI who has a time which can be distributed, and he decided to distribute this time by having an early science call, and certain programs have been accepted for 500 of hours. So that's the first data which has been taken and which are open to everybody. And you have the guest observer programs. That means every year there is a call, and you answer the call, there is a committee, and you get or you don't get your time. The pressure for the first cycle was about a factor 5. That means there were 5 more time asked for than possible. And we expect for cycle 2 to have a factor around 10 of pressure. So in the framework of one of these early science programs, there have been a lot of observation. And one thing which starts to appear is that there are much more galaxies than expected at redshift in the range 9-16. That's something which needs to be confirmed, but that's a tendency I think we can already claim. And the one thing also which has been confirmed is some to set this time spectroscopic observation instead of photo Z with imaging observation. For spectroscopy, there is confirmation that there are several galaxies further away than what Hubble has observed. So we already can say that one of the mission of James Webb to go and see the end of dark age will be achieved. So there will be much more observation, but we have already started to observe such kind of galaxies. And what is interesting is to compare where we are in terms of numerical simulation with the observation of James Webb. And for example, there have been recently an extreme horizons simulation of cosmologic simulation of the formation of galaxy with much better resolution than the previous simulation. And with the resolution, actually, this is an observed galaxy of James Webb, and this is the simulation which now are in which can reproduce what is seen by James Webb. So we have the tools to be able to run models and compare what James Webb find and what simulation produce, both with various parameters, which can be. Another thing which start to appear is the form of the galaxy. You know, galaxies can be with a bar and spirals, and we thought that such kind of feature would happen rather late in the evolution of the galaxy. But what has been found is such a shape of galaxy with a large bar and spiral early in the universe. So that's also something which is being, which is new and being assessed in terms of simulation, in terms of maybe rotation and so on. So there are already some puzzling observation, of course, which has to be confirmed with more statistics. But I am convinced that we will have very new observations, which will require some modification of the models. Just to show also a nice image of galaxy interaction. There is a lot of galaxy interaction, and that's trigger star formation. What important things is the evolution of the star formation in the universe, the rate of star formation. And here you can see some star formation induced by galaxy interaction. Just also a nice image to illustrate that we will learn a lot in terms of star formation. So this is a nebulae in which some stars form. And this is a cavity because there have been a massive star which has cleared this cavity. So a lot to be done in terms of evolution and other nice images. And what I really find extraordinary with such images is when you zoom, each time you zoom, you have a much more detail. So you cannot see all the details, but by zooming, you can really see that it is an image quality excellent. And all the field of astrophysics will be impacted by the James Webb observation. This is an image of Jupiter with what is called the red. Okay, but now I would like to spend some time on the exoplanet because it is a field I am working on, and James Webb will bring a lot of information. So just a general sentence about exoplanet. You know that we have now observed a lot of exoplanets, more than 5,000. And two words can be applied to such finding is diversity. We can really, here it is a semi-major axis. This is a planetary mass. And you can see that we have a lot of different exoplanets. And we find exoplanet almost everywhere, orbiting almost every star. So there are probably much more planets than stars because some stars have several planets orbiting them. So James Webb will not be another mission to find exoplanets. It will do something completely different. Webb is a unique facility to what I call the second chapter of exoplanet studies is a characterization of their atmosphere. And why observing exoplanet atmosphere? So we want to determine the molecular or atomic content of the atmosphere, the presence of clouds, hazes. We can determine the pressure temperature profile, determine the dynamics in the atmosphere, circulation, variability. All that is within the reach what can be done with James Webb. And why to have such information? It is important to constrain the model of atmosphere in a condition not present in the solar system. What are the physics, the chemical processes at work, cloud formation, and so on. Because we can see objects in exoplanets, we don't find them in our solar system. So we can push the models in a parameter range unknown so far, with no observational constraints. Knowing also the composition of the atmosphere for giant planets can give us some clue about where they were formed. If we have their mesolicity, sea overall ratio, all that is information about their formation. There is some degeneracy between the interior of exoplanet and the atmosphere. So knowing the atmosphere, we can better constrain the interior of exoplanet. And all that, the knowledge of the atmosphere, the physical and chemical processes can lead us to see something strange, especially for rocky atmosphere of rocky planets. And ultimately, there will be the search for biosignature. But I don't say that James Webb will see biosignature, but at least James Webb will really help to understand the physics and chemistry in this atmosphere. Two methods to observe the atmosphere of exoplanet. So the signal is very low, and we have to deal with the star signal. So either you use time separation, for example, transit, when an exoplanet is go in front of the star on the light of the side, you can see some decrease in the intensity, and then if you have spectroscopy in the infrared, you can see that the radius, if there is an atmosphere with some molecules, these molecules can also absorb light from the star, and you can see a larger region due to this absorption. So spectroscopically, you can see variation as a function of the wavelength of the radius of the exoplanet due to the atmosphere. So it's very little observation variation, but James Webb is very precise. We'll see some example, and you can do so. Another possibility is to have coronagraphic observation so that you prevent the starlight to arrive to the detector, and you can see what is around. In this case, it's exoplanet. And given the size of the James Webb, you have this possibility to observe by direct imaging some exoplanets. And this has been done. This is an example of an exoplanet. So this is with the near-term coronagraphic mode, so short wavelengths, and this is with MIRI. This is where the star is, and this is really the exoplanet. So it's the first time exoplanets are detected by direct imaging in this wavelength range. And it is important to have this wavelength range because most of the emission is in the MIRI range. So to have brightness, temperature, you need to have this information. And having the temperature, the brightness, you can go back to the evolution. This is relatively young exoplanets, and to have the way they have been formed, it can be retrieved, knowing more their temperature, their mass, and so on. For those exoplanets, so it's between an exoplanet and a brown dwarf, the limit is not always clear, but that's to show the spectrum in this case you can get with the spectroscopic mode of MIRI and short wave. All that is not noise, all that is the feature. So you have NH3, you have CH4, you have a lot of water, of course. So, the observation is so precise that now there is, I think the modeling is beyond the observations. And we can also see some isotopic ratio. For example, we have NH3 and 14 and 15. We can detect this kind of isotopic ratio. So that's really amazing what we can do. In terms of eclipse, so your eclipse or transit, so this is the transit and this is the eclipse. And this is one example of a spectrum observed for an exoplanets. And this was between 0.75 micron and 2 micron. So there have already been some HST observation in this wave range, but you can see water. It's really easy to see water in such giant exoplanets. And this was new, not new, but there have been some prediction with the observation of HST, prediction that you should have CO2 when looking at longer wavelengths. So we had some observation of this target, which is what was 39b. And indeed, we detected the CO2 feature in this atmosphere. This is fine, but it was predicted. So it's not so, so interesting to find what we predict. But beside this peak, you have here another peak. And this peak was not predicted. So we had to think, what could it be? And one candidate was SO2. And models had to add photochemistry in the atmosphere to explain the quantity of SO2. With the starlight, you can dissociate the water in the atmosphere, and you have this kind of chemical reaction which end up with SO2. So now, in some, it's not always the case, but for some flux from the star, you have really to include a sulfur chemistry, which was not included in the model so far. So that's one of the results. And of course, a theory should make some prediction. So this is what has been observed, and this is what is predicted. You should have also a very prominent feature of SO2 in the Miri wavelength. And we will have the observation next week. So we have asked to STCI to have what is called DDT time, to have time, because if you have really an object or something which should be done very rapidly, you can ask the director of STCI to do so. So it has been accepted, and we hope to have this feature observed soon. And then what we are also doing that is to try to find out why there is such a diversity. Can we find some law between the various parameters? So in our solar system, there is a law which was known since relatively long in terms of planet mass and the metallicity in the atmosphere. So we saw this law. And one exoplanet is right on this slope. So we say, oh, this is the law. But in fact, another one is completely wrong. And then we have to think about another way to combine parameters. So now we are trying the bulk metal fraction with what is in the atmosphere. So it seems to be a bit difficult. But it just to illustrate that we have still a lot of work and statistics work to be done before having a law. For example, for the evolution of star, the sequence of evolution of star, you need a lot of statistics. And we need also this for exoplanet to have really the law, the evolution law for the exoplanets. So this is an illustration of the transit. So you can see as a function of time, the flux, the signal, and this is the kind of transit you are looking for, the faint decrease because of the exoplanet going between you and the star. This is some detector drift, detector effect, which is called some systematics. But you can see that for a transit depth, that means that this variation here is 500 ppm, part per million. And if we look at the noise, it's 50 ppm, which is limited by the photon noise. So with James Webb, almost immediately, you can see this kind of transit. And this is what you were observing with Spitzer, which is only noise, systematic noise, and you have to use really sophisticated data reduction to obtain this kind of transit from such observation. And this variation here, it's about 5/300, a few percent. So it's enormous, a few percent compared to 500 of 50 ppm for James Webb. That's several orders of magnitude better with James Webb. And one reason for that is the stability of the telescope. For Spitzer, it was there is some jitter, stability of the pointing. And with the James Webb, here is a function of time. The variation of the pointing, variation of position of the object on the detector, and except here, where you know there is some movement of the antenna sometimes, but otherwise it's really perfectly stable. So this was for Giant planet, and now we have observation about rocky planets. And this is a famous system, which is the TRAPPIST system. This is an exoplanet relatively close to us, 12%. The equilibrium temperature is around 100 degrees Celsius. It's almost the size of the Earth and the mass of the Earth, and it orbits with an orbital period of 1.5 days. There are 7 such exoplanets, and some are in what we call the habitable zone, which means a zone where water can be liquid. And why this zone is so close to the star? Because this is a very little star. The radius is a bit larger than Jupiter, so it's a dwarf star. So that's very interesting to observe exoplanets around this such kind of star. And what we have done is to look at the eclipse. So when the exoplanet go behind the star, you have only the emission from the star. When it is close to the star, you have both the emission of the star and the planet. You make the difference and you have the emission of the planet. So that's what we did. And the result of that is a temperature much higher than the temperature of equilibrium. And we think the reason of that is that there is no or very little atmosphere. Why do we say that? These exoplanets are tidally locked to the star. That means that it is always the same face looking at the star. So you have a day side, and a night star side. And you have the day side, which is hotter than the night side, except if there is a good circulation of energy. And we can show from our measurements that there is no such a large circulation of energy. And how the energy can circulate, it's mostly when there is an atmosphere, with wind. So that's a first result about showing that we can detect the emission, the thermal emission of a rocky exoplanet. This sea has already been also observed. We have the temperature, and the idea is to go with the other one and to test up to those in the habitable zone. But it will it will imply a lot of eclipse, a lot of time to observe the temperature of these exoplanets. But at least we are showing the feasibility for these one, and we will keep on because James Webb is unique to observe exoplanets. Another very interesting exoplanet, rocky exoplanet, is this one, K2141b. Why it is interesting? Because it is at a very high temperature, almost to 2000 K, and we think that the rock is molten, and probably the Earth goes through such a phase when it was young. The Earth had certainly such a phase. So then we can have some equivalent of early Earth and see how such object, melt object, behave, how they have atmosphere, what kind of atmosphere. So that's also another very interesting object which is being observed. Another one is LHS 3842. We think there is no atmosphere, and what we plan to do is to observe the rock. What is this kind of rock on such exoplanet? So we have the possibility to do some geophysics on other exoplanets than the one in our solar system. So it's a perspective which are already realistic now. There is also some, we think, ocean world. We think that such exoplanet is made from water, ocean of water. So we will study them. This is GG 1214. And one interesting thing is to observe the full curve of an exoplanet. So eclipse when it goes behind, transit when it goes in front, and the variation as a function of time. And with such curve, we can measure the night side of the exoplanet temperature, night side temperature. So that's also take a long time in terms of observation, but to have both day side, night side, we'll have a complete picture of what is going on. So to conclude, I would say that James Webb works, which is normal after all the cost and so on. But what is really for me exceptional is the exquisite performance. It's better than specified that everything is at the best we could expect. That's what for me very unusual. And I really like the fact that we can probably observe many years, more than the 10. In fact, initially it was minimum 5, hopefully 10, and I would say hopefully now 25 years. So a lot will be done with this observatory, which works very fine. And thank you for your attention. And thanks a lot. Question from the room. Your exoplanet is 5 continents and radius of 1.3. Yes, you have a variation in terms of density. They are very variable. So you have some giants which are very low density, much less than, and you have some rocky exoplanets which are a bit denser than the Earth, maybe more iron. Yeah, really the diversity is really what can define these the exoplanets.
Yeah, I had 2 short questions. First one is about the sulfur. You said the sulfur was not included. I was wondering why it was not neither.
We consider that it was minor. The carbon chemistry was the most important one. In fact, you need carbon, you still have carbon. And sulfur was, because it's also much more reaction scheme to include and so on. So
what was the law you show where you had the system?
Yeah.
You say it was surprising that you have stroke, but this was the solar metallicity, I think. So why don't you show the stellar metallicity?
So in this one. Huh?
Yes.
So it was no, but oui, relative to solar.
Yeah.
I don't remember what was the metallicity of this star. I will check, but I think it's taken into account. So it's relatively solar. It should be relatively solar. But I think the star, yeah, usually we know, we know the metallicity of the star by spectroscopic observation and so on. Yeah.
Une étoile comme on rajoute, qu'est-ce qui se passe pour les autres détecteurs?
Alors, ça dépend. Quand on fait des transits d'observation, on veut que ça soit tellement stable qu'ils ne font rien. C'est seulement cet instrument qui observe. Dans certains cas, quand on fait des gros balayages du ciel, par exemple pour trouver les galaxies, là on met NIRCam et MIRI en parallèle, et comme on fait des grands champs, eh bien ça finit par passer, on finit par avoir les deux instruments sur tous les points du champ. On s'arrange. Donc là, c'est complètement intéressant d'avoir ça. Mais sinon, quand on regarde une étoile, ce qu'il y a à côté, il y a en général pas grand-chose. Alors, ce qu'on fait avec MIRI, quand on observe avec le spectro, on met l'imageur en route et on cherche des astéroïdes. Il y en a qui passent souvent. Donc, c'est un programme en parallèle d'observation MRS systématiquement, parce que les observations MRS, ce n'est pas des observations transit. On a l'imageur qui observe en même temps une autre région, mais pour les astéroïdes. D'ailleurs, quelque chose qui nous a vraiment surpris, c'est avec MIRI, tellement de grande sensibilité. On ne voit pas tellement des étoiles dans le champ, comme un plus court d'onde, parce que les étoiles, le flux diminue. Par contre, on voit des galaxies de façon complètement étonnante. Quand on faisait du commission, mais qu'est-ce que c'est que ces objets? Et c'est des galaxies. Tu as dans ton champ des galaxies. Incroyable.
There were 17 different operating modes.
Yeah, for the.
Have they all been characterized?
Yes.
And they all.
Yeah, exactly. Yeah. And it was a commissioning. So the commissioning was relatively long. In total, deployment, then co-phasing of the mirror, then instrument. It took 6 months to have all that commissioned. And after each mode, commissioning of each mode, we had a review in the CEA to say if it was good for science or not. And everything, so at end of June, the 70 modes was ready for science.
And are they all as good? I mean, you said you're 20% better than expected. All of them?
Yeah, because it's part of it comes from the telescope itself. So all have this. We had just one warning for one wheel of MIRI. At some point, we had an increase in the torque. So the observation were stopped to really understand what was going on. And in fact, it was always moved in the same way, same rotation. And after thinking what could it be, the operation has started again, and we are doing what was the other way, and it seems to work. So everything, mechanisms are really something. So I can see that one thing which has not worked properly, it was at the beginning of the deployment, when there were a cover for the thermal shield, so it's open. And normally there have been something to say it is open, and nothing. So during 1 day, everybody was, and then they realized that the temperature was decreasing. It was open, but so that's the only thing. And soon after they deployed it. Another thing which was a bit surprising, so it has nothing to do with the observatory itself, but we had a large, micrometeorite, larger than, it was only one, but it was at the beginning of the mission, and statistically we can say nothing, but we didn't expect to have such a large micrometeorite. And in fact, it damaged a bit one of the hexagons. Hopefully, it was possible to give back the shape, but there is a small impact. And this impact influenced the image quality, but as the image quality is 10 times better than the requirement, no, 2 times better, but sorry, you need 10 such micrometeorite to arrive at the requirement. But even with that, we are now avoiding the region where there are micrometeorite to prevent to have still some degradation of the optical quality. It has been taken not for the telescope mirror, for the thermal screen, but it has been taken into account. 4 layers would have been enough, but there are 5 layers to have some more. So in principle, it should be okay.
This is one way to look at this is that it's great for science, but from another point of view, it means that either we were very lucky or that many things were overviewed, over-designed, over-specified. And this cost a lot of money, a lot of time.
Yes. Yeah, that's a good question, indeed. It was really the flagship mission of NASA, and then a lot of care was taken. For example, for the Ariane 5 launch, they did the best they could in terms, for example, clean room, to don't contaminate the mirror. In terms of the, I heard that not all the rockets are exactly the same in terms of the components, so they took the best component. All was done at the best, and you have seen the launch is quasi perfect. So that's one part of answer for this part. Really, special care was done for this mission by Ariane, because it would have been a disaster if. And so that, in terms of, for example, for the telescope, it was really a challenge. So maybe people have taken some more margin than necessary, but it was really hard to say if we could decrease the margin by advance, as it was the really first time we had such a deployment. So margin had to be taken. So I don't think we could have decreased the margin to say it will be less, it will be cheaper, and it will also take some more risk. So.
Other questions? Or if you have questions on the room? Can you comment on the bias signatures, minus spec, or what are you looking for when you talk about bias?
Yeah. So some time ago, people were answering ozone. If, of course, on the Earth there is a signature by oxygen ozone, But in fact, in the star, like M star, the flux of the star is completely different. There are more UV, X-rays, and the question, and some people have shown that you can have abiotic formation of oxygen. So now it's more to have a combination of CHK, CH4 with other azote or things like that, nitrogen. So it's not a unique feature. It is a combination of two features which could not exist in some equilibrium or for some chemistry, natural chemistry. You should not have such a kind of component. So you say that something else, that's the normal chemistry. But you need to know what is normal chemistry. So that's why it would take really a long time to be sure that it is a biosignature, if there is something strange, which is fine. For example, SO2, rapidly we say that's photochemistry not introduced. So that's why I'm really careful with this question of biosignature. I know some people from James Webb say, James Webb, no, be careful. Already knowing what is going on in the atmosphere in terms of physics, chemistry, that's already an achievement. You know, we are going step by step, approaching the question of biosignature. So the first exoplanet was detected in 1995. It was giant. Now we have a rocky planet. Now we can observe atmosphere in rocky planets. We have also some rocky planets in the habitable zone. So we are progressing, but we cannot go very far. We are going step by step. And I think with James Webb, we have this step of probing atmosphere of exoplanet, of rocky planet. Are there atmosphere or not? So that's this step by itself is already a huge step for me. And biosignature is still further away.
A question concerning early galaxies. The total beginners are much more than expected. So is there really statistically significant?
No, I say be careful with that. That's the first tendency which appears. Some are not still done with spectroscopy observations, that just photosynth, which have some uncertainty. So it's just the beginning. So we have better to be careful.
Will be another same breakthrough?
Yeah, and there will be new observations, new results. So because it's going relatively fast, so I'm sure it will be interesting and give you more facts.
Whether the limits of what you call normal MS, right?
That's a difficult question. That's what. So now we have chemical change, for example, in the atmosphere. It depends on the temperature, but I think the carbon chemistry is well known, and there have been some laboratory measurements from people with motors. So there are some what is going on in motors in terms of carbon chemistry and so on. So we have some good laboratory measurement in terms of the various chemical with carbon. But for example, with sulfur, I'm not sure we are at the same level of knowledge in terms of temperature. We know well what is going on within the Earth's temperature, but in exoplanet you have higher temperature and so on. So that's where I see even what is normal still need some more laboratory measurement and so on. I cannot yet answer exactly what is normal because there are still parameters which has to be measured to and also there are several models of the chemistry in such atmosphere which don't give all exactly the same results. So there are still a lot of work in terms of modelization to be sure that we have the right modelization. And there is all the question also of opacities. There are a lot of measurement of opacities going on because it's atmosphere and you need the opacities to see what would be the result in terms of spectroscopy. So that's why I think the atmospheric models need opacities, need chemical, what is the chemical reaction, and that's still going on. So I don't think we are still at the normal. We are still defining what is the normal. And we need also observation to see if we can fit the model with the observation with what we call now normal. And if there is something abnormal, is it because the model are not enough complex, or is it something because of the model, or is it something really because there is non-equilibrium? So that's the question we will develop with James Webb. But I cannot say yet now what is the normal chemistry. There's still a lot of parameter studies to be done before saying this is the normal one.
Yes, yeah. Thanks for the presentation. And maybe the last question, we have talked a lot about the results observed in the exoplanets. Is there any interest in observing the exomoons, or at least for the French community?
Exomoons, I know there are people like Sébastien Charnoz who are looking for exomoons with the Chaos Observatory. With James Webb, I've not seen yet public proposal doing so. There have been in terms of exoplanets being built in disk. It's not yet moons, but we think there are disks around this exoplanet. And disk in the infrared can really have a significant feature. So that's also difficulties to disentangle what could be from the exoplanet itself or from its disks. So there will be some studies about this kind of object, but more in, at the moment at least, more in still exoplanets still in the disk, where they can accrete some in the protoplanetary disk. They can still accrete some material to get rings or disk around them.
Last questions? Okay, not again.